Everyone, welcome back. Let's try another problem with some stress and some strain and other little concepts here from chapter 6. So in this problem we have a bronze alloy. It says the stress at which plastic deformation begins is 261 megapascals. And the modulus elasticity is 114 gigapascals. It's asking for two things. First off, what's the maximum load we can have? Okay, what's maximum force? With a cross-section 343 millimeters square without plastic deformation. And if it has this length right here, what's the maximum length that it can be stretched to without also causing plastic deformation? So let's talk about a few things here. First off, plastic deformation. What is plastic deformation? If you don't know that, I'll go ahead and show you. So we'll have a stress strain curve that looks something like this. Okay? And my stress strain curve, this is stress right here, this is strain. The cool thing is this place right here is the linear section, and its slope is actually equal to E. Okay? Slope is E. That's really nice. I say E, I mean the modulus elasticity. Now, initially, if I were to stretch something, so I pull it out here, if I let go, it will just release all of that energy and go back down. There is a certain point, though, where I go from being a linear, straight line to a curved line. You kind of see it like up here, okay? And that's the point where it begins to yield. And so when I say yield, it means that if I were to stretch it too far, it would not be able to unstretch all the way. So some of that stuff would be left in there. That is what's going to be called my plastic deformation. And that's not always a bad thing. We actually do plastically deform things on purpose. Like you've probably seen, movies where you have the blacksmith and he's puts the sword down on the anvil and then he begins to smack it with the hammer. Repeatedly smacking it with the hammer. Why is he doing that? Well, he's actually plastically deforming it. And he's forming it too. There's a lot more that goes into this here, but I'm giving a very simple example. So doing that, beating it, is plastically deforming it, and it's making it harder and stronger, which can be very good for it. There we go. Okay. So right here, when it says when plastic deformation begins, what it's giving us right here is actually what's called the yield stress. Okay? And so that's good to know. So the maximum load that we applied to this thing is saying what is the force when we're at our yield stress? Okay? What is the force when we're at our yield stress? So for this one right here, let's see here. Stress is equal to force over area. I'm just going to add some y's here so you get that that's the yield force and the yield stress. And so I can rearrange, then I get my force is equal to my stress times the area, which would be equal to 261 megapascals times 343 millimeters squared. As a note, you can switch everything to pascals if you want to, and meters if you want to. However, megapascals and millimeters squared, they're just a match made in heaven, because 1 megapascal is equal to 1 Newton per millimeter squared, which means that if I multiply these together, what I get then is going to be newtons. I can convert that if I want to. So if I plug this in, I'll get that it's 89,500 newtons, or if I wanted to, I could say 89.5 kilonewtons. So that is the force at which it would have plastic deformation, which means that any force beyond that will stretch it just enough that when I let go, it will not unstretch all the way. Whatever I went past that will be stuck in there. Okay, now how about this second one? We're trying to figure out, well, how much can it be stretched before it deforms? So with this one, we're going to be doing a very similar thing. We have a yield stress. Well, then guess what? There's going to be a yield strain too. So stress is equal to the modulus elasticity times the strain. And so if I rearrange here, I can solve for that. Okay, so my strain when it yields is going to be equal to my stress when it yields over the modulus elasticity. So let's go ahead and figure out what that strain would be. Let's see here. My modulus elasticity is 114 gigapascals. Okay. So this would be equal to 261 over 114,000 1,000. These are both megapascals now. I'm not writing the units because they're just going to cancel. And so let's see what that comes out to be when I plug it in my calculator. And that comes out to be 2.29 times 10 to the negative third. Okay, now what is strain? Well, strain is equal to my change in length over my original length. Or I could write that slightly differently. I could say that's equal to my final length minus my initial length over my initial length. You get where I'm going here? Well, do we know our initial length? Let's see here. We do. It's 137 millimeters. So that means that currently, for this little equation here, we know everything except for our final length. So we can solve this. So let's rearrange it a little bit and get this done. So what I'll get then is my final length is going to be equal to, multiply this guy across, okay, the strain times my initial length plus my initial length. Okay, I told you written that down. I think it was 137. I was right. So my final length will be equal to 2.29 times 10 to the negative third times 137 millimeters plus 137 millimeters. It's not going to be like an insane number here. You're always stretching it very, very small amounts. So in the end, we get a grand total of a glorious 137.3 millimeters. Remember, you don't really stretch metal all that much. Like 0.3 millimeters is a long way to stretch something. Now this is 137 millimeters long, so might not seem like much to you, but it's quite a bit for metal. Because rubber band will be much further. But with that, we figured out the length we could stretch it to when it would begin to yield. And if it had been a longer length, well, it would have been a longer point before it yielded. Okay, so that's it for this time. Hopefully this helps you. Thanks for listening. I'll see you all later. Bye-bye.